All right, picture this for a second because it's actually a pretty terrifying scenario. You're looking out your window, right? And hovering anywhere from 2 to 5,000 meters directly above your head are dense, rolling storm clouds. Now, intuitively, we know that if you drop a simple solid object like a rock or even a heavy coin from a fraction of that height, say a skyscraper, it is going to violently accelerate. By the time it hits the pavement, it's traveling fast enough to literally crack human bone. And yet, during a storm, billions of water droplets are falling from those exact same catastrophic heights, and we just casually stroll outside with an umbrella. To figure out how we survive this on a daily basis, we're going to treat this explainer like a forensic case file. We'll quickly run through Part 1, the deadly rain paradox, Part 2, the mathematics of drag, Part 3, terminal velocity reached, Part 4, the hailstone threat, and finally, Part 5, our invisible shield.
Starting with Section 1, the deadly rain paradox. Let's strip away everything and just look at the raw, unyielding Newtonian physics of a typical afternoon storm.
Because look, gravity is just a relentless engine, right? It accelerates falling objects at a terrifying 9.8 meters per second squared. That means for every single second an object is in free fall, it is gaining nearly 10 meters per second in downward speed. It's a compounding, destructive force.
Do the math on that from the altitude of a storm cloud, and a single heavy raindrop should logically be hitting the pavement at over 700 kilometers per hour. Think about that. That is faster than the cruising speed of some private jets. At that kind of velocity, every rainstorm would literally be a deadly machine gun barrage, shredding leaves, shattering windows, and destroying anything caught outside.
So why doesn't it? If the pure math says rain should fall at 700 kilometers per hour, why doesn't rain kill us? What unseen mechanism is stepping in between the cloud and the ground to save our lives? Well, welcome to the Math for All channel, where we are breaking down this exact scientific mystery today. We're pulling some fascinating data from MIT's Dr. Smith to map out exactly how physics steps in to save you every time it rains.
Moving right into Section 2, the mathematics of drag. Dr. Smith introduces us to the real invisible hero of our story here, which is air resistance.
See, we tend to think of the air above us as just empty space, but it's absolutely not. Thanks to fluid dynamics, we know our atmosphere is actually a dense fluid packed tightly with billions of microscopic gas molecules. When a raindrop falls through the sky, it has to physically plow its way through that dense molecular soup. The air is actively pushing back against the water.
So this sets up an epic mathematical tug-of-war deciding your fate. Pulling down, you've got gravity, or FG, trying to accelerate that drop to lethal speeds. But pushing back up, you have FD, aerodynamic drag. And Dr. Smith's breakdown shows us that this upward push relies heavily on the fluid's density, the square of the object's velocity, and crucially for our story, its shape. And this brings us to a brilliant morphological twist. It's the secret weapon of water. We always draw raindrops as perfect little teardrops, right? But fluid dynamics tells a totally different story. As the drop speeds up and smashes into the air below it, the intense wind resistance actually squishes the bottom of the drop. It flattens out from a classic tear shape into something that looks a lot more like a hamburger bun. That distortion drastically increases its surface area, which violently amplifies the air resistance pushing back against it.
Now, right before we reveal the exact formula that neutralizes gravity and saves your life, do me a huge favor and hit that like button. Drop your thoughts on this crazy paradox in the comments, and make sure you subscribe to the channel so you never miss our next explainer. All right, Part 3, terminal velocity reached. Let's look at the climax of our physical narrative. What mathematically happens when these two massive forces finally collide in the middle?
This is the mathematical breakthrough that totally caps the raindrop's lethal potential. Terminal velocity isn't just a buzzword, it is a beautiful, life-saving moment of equilibrium. It's that exact microsecond when the upward smash of aerodynamic drag completely cancels out the downward pull of gravity. Because the net force becomes zero, acceleration just drops to zero.
It comes down to this really simple but profound equation, Fg equals Fd. When gravity perfectly matches drag, acceleration is nullified. Yes, the object is still falling, but it just cannot speed up anymore. Its velocity is locked in. The atmosphere has effectively slammed the brakes on the raindrop.
So what is that magic locked-in speed? For a typical 2mm raindrop, once you calculate that flattened hamburger bun surface area against the dense air, it locks in at a surprisingly gentle 9 meters per second. That's about 32 kilometers per hour. And because it reaches that speed in just a few seconds, it honestly makes absolutely no difference if the cloud is 2,000 meters high or 10,000 meters high. The math caps the speed, making it completely harmless by the time it bounces off your umbrella.
But let's look at Section 4, the hailstone threat. Because what happens when we introduce a horrifying edge case? What happens when we tweak the drag equation and look at frozen rain?
This is the physics of a nightmare scenario. Because hail is solid ice, it's dense, it's heavy, and it's rigid. It completely skips that life-saving hamburger bun transformation. It physically cannot flatten out. And without that extra surface area, the upward aerodynamic drag is severely handicapped. The hailstone has to fall much, much faster just to build up enough wind resistance to finally match its massive gravity.
Just look at the contrast in this data. Water is a fluid that flattens out, capping its speed at 32 kilometers per hour. But ice remains rigid. That inability to increase surface area means a large hailstone gets pushed to a terrifying, car-denting terminal velocity of 160 kilometers per hour or more. This perfectly explains why rain is just a mild inconvenience, while a hailstorm is a destructive event that totals vehicles and ruins crops. The math of drag shifts entirely out of our favor.
Which brings us to our final takeaway in Section 5, our invisible shield. Pulling it all together, the air we breathe does so much more than just fill our lungs. As Dr. Smith so perfectly stated, without the mathematics of drag, life on dry land would be ecologically impossible. Without our atmosphere balancing the equations of gravity, life on land would quite literally be battered into extinction. It acts as an immense, frictional brake against trillions of tons of falling water every single day.
And that leaves us with a pretty haunting question, doesn't it? If our atmosphere is this highly calibrated, invisible shield protecting us from the brutal physics of the universe, what other lethal forces is it secretly fighting off right now? Let me know your best theories down in the comments. Smash that like button if this changed how you view a rainstorm, and make sure to subscribe to Math for All for our next explainer.